Reaction stoichiometry. How much carbon dioxide? So if we had an estimate of an amount of petroleum products that were burned every year, could we calculate how much carbon dioxide was being given off? We could. And that's a technique called stoichiometry. So we have this balanced chemical reaction that provides exact relationships between the amount of fossil fuel burned and the amount of carbon dioxide given off. So, this is balanced. And what we see is that for every 2 of these molecules, what do you suppose the name of this guy is? C8, H18? Octane. It's got 8 carbons. So for every 2 of these molecules, we're going to get 16 carbon dioxide molecules. So that's counting individual particles. Well, there's an awful lot of particles. The mole is more useful. The mole is the chemist's dozen. So we can also put in 2 moles of this would produce 16 moles of that. If that bothers you, think dozen. 2 dozen would produce 16 dozen. The mole is just like the dozen, it's just a number. In that chemical reaction, the amount of every substance that's used up that reacts and the amount of every substance that produced is related in the balanced chemical equation. Because, like I said, it's like building with Lego blocks. You take these apart and you put them together in a different way. You can predict how much will be formed. And important concepts here are the law of conservation of mass, that atoms aren't appearing or disappearing, and that we have a balanced chemical equation. So this crazy word, stoichiometry, is studying the numerical relationships between chemical quantities in a reaction. And this is an important part of chemistry and one of the big reasons that you need to know how to do dimensional analysis. So when we look at a chemical equation, the coefficients, those are the big numbers in front, specify relative amounts in moles of each of the substances. So this can be interpreted on a particle level. 2 molecules react with 25 molecules, or in terms of moles. 2 moles of this react with 25 moles of that. So this gives us ratios of particles, ratios of moles. It does not give ratios of masses. It has to do with particles. And so we can come up with ratios: 2 moles of octane to 25 moles of oxygen to 16 moles of carbon dioxide to 18 moles of water. And from this ratio that's coming straight out of the coefficients in this equation, we can find the relationship between any 2 reactants or products. Making pizza. The other book talks about making pancakes, which for this class would be more appropriate, but let's think about making pizza. So the number of pizzas that you make depends on how much ingredients you have, right? So if we use this as a very primitive recipe, 1 crust and 5 ounces of sauce and 2 cups of cheese makes 1 pizza. There's a ratio here, 1 to 5 ounces to 2 cups to 1. And we can use this to calculate how many pizzas we could make if we had 10 cups of cheese. Now, you may be able to look at that and just say, oh, 5. But maybe not. It's helpful to see with something that is familiar how we can use these ratios to predict this. So if we have 10 cups of cheese, we can make a conversion factor from that equation or from the ratio and figure out how many pizzas. So we look here and we see that there are 2 cups of cheese needed for every 1 pizza. That's the relationship. Here we're going cups of cheese to pizzas. We're going to use dimensional analysis and put the units in, pizzas and cups of cheese, so that the units work out. What's the relationship between cups of cheese and pizzas? 2 cups of cheese for 1 pizza. And so we've got 10 times 1 divided by 2 is 5. Now we can see that looking at the equation. But this is how you write it out. Does that make sense? Because if it makes sense here, then there's hope for it making sense when it's moles of hydrogen or grams of carbon. We can do a similar thing with the balanced chemical equation. But now we're not looking at cups of cheese and pizzas. We're looking at moles of this and moles of that. So those conversion factors come from the balanced chemical equation, and they relate moles of reactants and products to each other. Any 2 in the equation. So we're going to stick with this burning of the octane. If we burn 22 moles of octane, how many moles of carbon dioxide will form? This is the same as the cups of cheese pizza question, but with weird things. Well, 22 moles of octane. And what are we trying to figure out? Moles of carbon dioxide. The beauty of this is this moles to moles is always just one step. So we put the units in first. 22 moles of octane, we're going to multiply by moles of carbon dioxide, divide by moles of octane. The numbers come directly from the coefficients. 2 moles of that, so we've got a 2 in the denominator. 2 moles of this will form 16 moles of that. Now, yeah, you could simplify that and say, well, it's times 8. I don't think it's worth the mental effort to do that. Just punch it through in the calculator. Because sometimes when you do that stuff in your head, you make mistakes. And it's just a dumb way to lose points on an exam. So, 22 times 16 divided by 2. Well, that's not right. 107, well, maybe it is. 176? Mm-hmm. Yeah, 176. How many significant figures should that have? 3. Our starting number of moles had 3 significant figures. These coefficients are exact because exactly 2 molecules of this form exactly 16 molecules of that. There's no uncertainty at all. And when you multiply that by a mole, it's still exact. So the coefficients never change the number of sig figs. Any questions? Well, moles to moles is nice, but we usually measure things in grams, right? There's no balance that measure moles of anything. So this is our general conceptual plan for stoichiometry. What we just learned how to do is, if we have moles of one substance, figure out how many moles of another substance. That is at the core of stoichiometry. That's always going to be present in the middle. Moles of one thing to moles of another comes from the balanced chemical equation. But if we have moles of this product, can we figure out the mass of the product? Yeah, we just need to use the molar mass, which we calculate using the chemical formula and the periodic table. And if we want to know moles of A, we can have mass of A, again, converting mass of A to moles of A, just using the periodic table and the formula. So that's one way to say it. grams to moles to moles to grams. So you should chant that. You know you've got it when you wake up in the middle of the night mumbling grams to moles to moles to grams. That's the path. We talked with dimensional analysis about finding the path from the beginning unit to the ending unit. Finding the path is the hardest part. Then it's just a matter of details and following a pattern. This is your path for mass to mass conversions. If we have a mass of octane and we want to know the mass of carbon dioxide, this is the path. Grams to moles to moles to grams. So here's an example pertaining to that idea of the greenhouse gases and global warming. So according to the U.S. Department of Energy, the world burned 3.1 times 10 to the 10 barrels of petroleum in 2010. Is that an exact number? No, that's an estimate, okay? That's an estimate. That's a 3 with 10 zeros after it. And the uncertainty is here in the ones in this 0.1. So very, very broad number. That's the equivalent of about 3.5 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. We can calculate this. We're not going to get a super precise number because we're making several assumptions. First, we have an estimate of the number of barrels of petroleum. Secondly, we're saying, well, let's just say that all of that was gasoline, and this would be the mass of gasoline. And then gasoline is a mixture of many different compounds. We're saying, well, let's just pretend it's all octane. So there's a lot of estimating in here, but it'll still give us an idea. So here's our equation, hopefully now familiar, the burning of octane. So here we have a mass of gasoline, but it says use octane as your reactant there. So I like to use the chemical equation to help me organize my information. So I've got 3.5 times 10 to the 15 grams of gasoline, and we're pretending it's all octane. So I'm going to write that under the formula for the octane. So I've got this many grams of that substance. I am trying to find grams of this substance. So what I'm doing in my path is I'm going grams of this to moles of this to moles of that to grams of that. I'll draw the path up here on the top because I'm not going to have enough room. So grams of C8H18 to moles of C8H18 to moles of CO2 to grams of CO2. Grams to moles to moles to grams. It does not work moles to grams to grams to moles. That does not work at all. So I've got my path. I have 3 arrows. I'm going to have 3 conversion factors. I'm just going to follow the pattern. 3.5 times 10 to the 15th grams. It's important here to write grams of what and moles of what. C8H18. And on the next line, I'm going to have moles of C8H18. And on the next line, I'm going to have moles of CO2. And on the final line, I'm going to have grams of CO2. Grams to moles to moles to grams. And then we do the same thing we did before. We take the previous unit and bring it into the denominator because we want to cancel those guys out. And this will be moles of C8H18. And down here, this is moles of CO2. Any questions? So we need to come up with numbers for 3 conversion factors. I like to start with the easy thing first, right? The one in the middle is the easiest. The relationship between moles of CO2 and moles of octane. That comes from the balanced chemical equation. 2 moles of C8H18 will make 16 moles of carbon dioxide. So I've got 16 moles of CO2 for every 2 moles of C8H18. No calculating. Look at the balanced chemical equation. The other 2, we need molar masses. Okay, so C8H18. We've got 8 times the mass of carbon, 12.01, plus 18 times the mass of oxygen, 1.008. 114.224. So 114, let's leave a little more space there. 114.224. Now we should always be concerned about significant figures, but we do not want to round a molar mass in the middle of a calculation. If that was our end result, what's the molar mass, we'd round it. As I did it, I used 4 significant figure molar masses, and so this technically would have 4 significant figures. I'm just going to underline that too, just to keep track, but I'm not going to round that off. And then there's carbon dioxide. So carbon, 12.01 plus 2 times 16, that's 44.01. Now we just go straight from left to right, times the top, divide by the bottom. Make sure that you enter your scientific notation correctly. We've got 3.5 EE15 divided by 114.224 times 16 divided by 2 times 44.01. And that would have 2 significant figures because of our starting number. So that will come out to 1.1 times 10 to the 16th grams of CO2. Anybody else get that? You got to the 6th? Try it again. So easy to make a mistake. It's worth punching it through twice on your calculator. Or if you have one that displays what you've done, you can go up and look. And you probably left the 1 out of the 15, right? Yeah. This is a really big number, but it's reasonable because we started with a really big number. Okay? That's a lot of carbon dioxide. Compare that to volcanoes. Volcanoes produce about 2 times 10 to the 11th kilograms of carbon dioxide per year. I think I've got the next slide. Okay. So here is, here's our result. I meant to delete that other thing. So here's the result we came up with. 1.1 times 10 to the 16th grams of carbon dioxide per year from petroleum combustion. Volcanoes, here I've converted it to grams just to make it a little easier. 2 times 10 to the 14th grams of carbon dioxide per year. I'm like, Well, let's find out what percent is the volcano production of the petroleum production. So let's take the volcanoes, 2 times 10 to the 14th grams, and divide by the petroleum combustion. And as a percentage, so 2 EE14 divided by 1.1 EE16 times 100. I'm getting 1.8%. With sig figs, that's 2%. So 2%, the volcano production is 2% of the petroleum production of carbon dioxide. So this increase in carbon dioxide levels, is it due to a natural source or due to humans? probably due to humans, right? Because we're producing a lot more carbon dioxide than the volcanoes are. Any questions? I hope that also, besides teaching you stoichiometry, gives you just a picture into how scientists think about numbers. There's just so many different facets of looking at numbers like that. Does this prove anything? No, doesn't prove anything. Does it give us some hints, some suggestions? Yeah, it does. Okay, here's another practice problem. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl. Did you know you have hydrochloric acid in your stomach? You do. And it's a good thing, because otherwise you wouldn't be able to digest your food and you'd die of malnutrition. You've got acid in your stomach. According to this reaction, and here, the point of this is stoichiometry, not balancing equations, so this is already balanced for us. The question is, what mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? Well, we're given this balanced chemical equation, and we're given this mass of magnesium hydroxide. Well, let's write that under the formula in that balanced chemical equation. I find this is the easiest way to just organize the numbers, and so I can get an idea of what's going on. I'm a visual person. I need to see things. And so some things you can actually write down and see, and other things you have to use your imagination, right? And so I have this like chemical imagination, and that's why I'm sharing with you the Lego bricks and stuff. In my mind, I'm visualizing these things being put together. So 3.26 grams of that guy. Then what's the question? Mass of HCl in grams. So question mark grams. Because it's a shame to go through all the work of calculating something only to find out that you calculated the wrong number. Because we could also calculate mass of water produced or mass of magnesium chloride produced. But that's not what we're trying to do. So we're going from this one to this one. This time it's two reactants. Last time it was a reactant and a product. It can be any two. So what's our path? What do we chant? Grams to moles to moles to grams. This is the one with the number. That's where we're starting. This is the one with the question mark. That's where we're going. So grams of this to moles of that to moles of the other thing to grams of that other thing. So 3.26 grams of magnesium hydroxide. Writing all the chemical formulas can get very tedious. I agree with you. Do it anyway. After you successfully complete my class, if you want to stop, that's fine. But in my class, write them down. So I'm going to go from grams of that to moles of that. And then I'm going to go to moles of the other thing, moles of HCl, and then to grams of HCl. And I bring the units around to cancel out. The units tell you exactly what to do. It's just so beautiful. I know I'm crazy. Three terms. We need numbers. Middle one's the easy one. Balanced chemical equation. 1 mole of this gives 2 moles of that. 1 mole of wrong fraction. 1 mole of magnesium hydroxide, 2 moles of HCl. Then we need the molar mass of magnesium hydroxide. Magnesium is 24.31. I should do what I tell you to do. You really should write this down. So 24.31 plus, there's 2 oxygens, 2 times 16, and 2 hydrogens, 2 times the mass of hydrogen. Sometimes if you're just thinking it and punching it into your calculator, you can accidentally skip an element and come up with the wrong mass. So 24.31 plus 2 times 16 plus 2 times 1.008. 58.326. Anybody else get that? Yeah. Okay. 58.326. And that would have 4 sig figs. That's the mass of 1 mole. So 1 mole of magnesium hydroxide, 58.326 grams. And then for HCl, we've got 1.008 plus 35.45, which gives us 36.458 for the HCl. Did I do that one right? And then you go across 3.26 divided by 58.326 times 2 times 36.458 equals. And how many significant figures should this have? 3. Because we started with 3. This one has 4. This is exact, and this last one has 4. Yeah, I did underline that. So I'm getting 4.08 grams of HCl. Anybody else? Okay. Any questions? There's no shorter way to do this. It's just going to take 3 steps. Once you get the hang of it, though, you can whip these out really fast. Peek ahead. Okay. One more example, and then we'll stop for today. A component of acid rain is nitric acid, which forms when NO2, which is also a pollutant, reacts with oxygen and water according to this simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate O2 and H2O, what mass of HNO3 in kilograms can form from this amount of NO2 pollutant? Lots of words, lots of chemical formulas in there. Wow! Anybody feel like that? Yeah. Thank you for being honest. Well, we've got a balanced chemical equation. There's only one number in there, right? The numbers are really important. A lot of the words we could completely do without. Like this whole thing up here, very nice and informative and everything. Do we need to know that this is about acid rain? No. The bottom line is 16 kilograms of NO2, and the question is what mass of nitric acid? So we've got 16 kilograms of this, and the question is what mass of HNO3? Let's take that and write that under the formula. 16 kilograms. And the question is, how many kilograms of that? Everybody okay with that? Bless you. I'm not going to have enough space here. We do not need all this stuff at the bottom anymore. Isn't that fun? There. Now we have some space. We've got a mass of one substance. We need a mass of another. The path is grams to moles to moles to grams. But we have kilograms. So there's two approaches we could take. We could ignore the kilogram-gram problem for now, or we could deal with it. This is one of those situations where procrastination is rewarded, and if you decide to deal with it later, we will see that we don't actually need to deal with it at all. So that's what I'm going to do, because that's kind of how I approach life. It's working mostly. So 16 kilograms of NO2. We're going to ignore him for right now, okay? We'll write him in there, but we're going to pretend he's not there. So we're pretending it's grams of NO2. That goes to what? Moles of NO2. And the next one is moles of HNO3. Somebody else could contribute to this as well. And what's the last one? Grams of HNO3. But it's kilograms. There's our kilogram that we're ignoring. Let's see, we're trying to find kilograms here. Okay, so again, ignoring the kilograms, we'd have grams of NO2 down here, and moles of NO2 down here, and moles of HNO3 down there. Okay, now let's think for a minute about our units. If I have kilograms up here and kilograms over there and grams down here, are those going to work out to be kilograms? No. This gram isn't going to cancel either one of those. What if I, oh yeah, shoot. Oh yeah. You got to be careful when you do tricks. What if I leave that as gram? How are those mass units going to work out now? Grams and grams are going to cancel, and the unit that's going to be left is kilograms, right? So that's going to be okay. So I've got moles of HNO3 canceling, moles of NO2 canceling. I've got the NO2 masses canceling there, but the gram is canceling up here, and I'm left with kilograms of HNO3. Hopefully that was not confusing. I think it was. What goes in the middle fraction? It's the mole-to-mole ratio, which in this case is 4 to 4. How about moles to grams of NO2? Well, we're going to calculate molar mass. 14.01 plus 2 times 16.00. I was going to do that in my head, and then I realized my head is not cooperating. 46. So 46.01 down here. And then over here, we need the mass, molar mass of nitric acid, 1.008, plus the nitrogen, and 3 oxygens. $63.0818. Did I do that right? 63.018. So 16 divided by 46.01 times 4 divided by 4 times 63.018. We should have 2 significant figures in our answer, and so 21.914 blah blah blah, it rounds to 22. 22 kilograms of nitric acid. That's a little disturbing when you think about it, isn't it? Unless you've got solar panels, generating enough electricity for one home for a year is going to generate 22 kilograms of nitric acid that goes off into the atmosphere. Any questions?